Greetings and welcome to Lecture-12. So far, we have studied various problems on material balance, which involved chemical reactions, which were without chemical reactions. We also applied our knowledge on material balance on a process called combustion, right? So we have done a lot of problems on material balance. So I assume that you people have by now been clear with material balance related issues. Now we'll move on to the last topic for chemical process calculations, which is recycle, bypass, and purging. All right. Apart from that, uh, even energy balance comes under chemical process calculations, but we'll study that under thermodynamics. So this is going to be the last topic for chemical process calculations, that is recycle, bypass, and purging. So these three are very important unit operations, and they are very they find quite enough application in the industry. All right. So we'll first of all come to recycle. So basically, you people have studied so far that, let's say, we have to conduct a unit operation. So for that, we have a unit. All right. In that unit, we send something in, we get something out. All right. Whether it involves chemical reactions or whether it does not involve chemical reactions, in each case, you send something in and you obtain something, right? Now, whatever you obtain over here, it may be very properly processed, but it is possible in most of the cases that the stream that you're getting out, it's not properly processed, right? Also, in certain cases, we have to send some of the stream back in order to increase the efficiency of the process. All right. So in all cases, what we do is over here, we have a separator. We have a kind of a separator which separates a small part of the product stream and sends it back. Okay. It separates a small part of the product stream and sends it back. And over here at this junction, it merges with the incoming stream. All right. It merges with the incoming stream. All right. So this stream is known as recycle stream, and the process is known as recycling. All right. This process is known as recycling. So in recycling, this over here, the stream which is not mixed with the recycled product, this part, before it is being mixed with the recycled stream, before that you have this stream, it is known as fresh feed. Okay, this is known as fresh feed. All right. Then over here, after the two have been mixed, so over here you get mixed feed. Now mixed feed is basically the recycle plus the fresh feed. All right. Then from unit, after processing, over here you get the process feed or processed product. Okay, here you get the processed product, and after two you get finished product. After two you get the finished product. This is whatever the final thing you withdraw. Okay, this is known as recycling. This entire thing is known as recycling. So for example, the most commonly seen example of recycling is in a distillation column. So what happens in a distillation column? Suppose this is your distillation column and this is your feed that has entered. Now, as I told you, from the top you get vapor, which is rich in the more volatile component, and from the bottom you get liquid, which is rich in the lesser volatile component, right? So over here, whatever the vapor it comes out, it is made to pass through a condenser. Okay, it is made to pass through a condenser. So this condenser, it condenses this vapor into liquid form. Okay, now this, out of this liquid, some of the liquid is sent back, while the remaining, it comes out. Okay, so the remaining liquid, that is remaining, whatever has been drawn out, that is known as your distillate. And whatever has been sent back, that is actually the liquid. Okay, the recycled liquid. Okay, so here recycling takes place in order to increase the efficiency of this process. All right, in order to increase the efficiency of this process. So when you'll study the process of distillation in detail, calculations related to distillation, then you'll realize how important this recycling is. Okay, so basically this recycle, it increases the efficiency of this process. All right, so that's the importance. And for this, you get a reflex ratio R, which is basically the amount recycled upon distillate, that is the amount, the product. All right, so in general, you people will be coming across this term in recycle based problems, that is reflux ratio. So reflux ratio is basically recycled, amount recycled upon amount that has been withdrawn as product. Okay, and there is something also called mixed feed ratio. Okay, you might come across this term as well. So mixed feed ratio is basically, here you have the mixed feed, so you get it as recycled upon mixed feed. Okay, recycle upon mixed feed. All right, so now when we talk about a recycling operation, so recycling operation has too many scopes for material balance. So for example, you can enclose this entire system, the entire system, into a system boundary, a control volume, as we discussed in few classes of material balance without chemical reactions. You can enclose this entire system into a system boundary or a control volume, a fixed volume. So then you will have this entire unit. You will have fresh feed coming from here, and you will have finished product going out of here. All right. So one scope for material balance is this. All right. Then the second scope for material balance is around this unit. Okay, around this unit. So what you can do is you can have your unit. You can have this as your unit. And then over here you have your mixed feed. And over here you have the processed product that has just come out of the unit. Okay, remember F and M and P and P1, they are different. Okay, so this is how you can do material balance about this unit. All right, then the third scope for material balance is at the 2 points, that is point number 1 and point number 2. So at point number 1, if you see, so let's say this is your point number 1. Over here you get fresh feed. Over here you get mixed feed. And from here you have recycle stream coming. Let's call it R. Forget about the fact that R is reflux ratio. I've just mentioned it over here because this is how you denote reflux ratio in distillation. Okay, but for now, just forget it that we have said anything called reflux ratio in distillation, or basically forget about the fact that reflux ratios are in distillation column. So R is basically the mass or molar flow rate of the feed stream, of the recycle stream. Okay, so this is the scope of material balance about point number 1. And similarly about point number 2, if this is your point number 2. So R, then you have processed product and your finished product. So altogether, you can have 4 different material balance equations. So there are 4 scopes for material balance in recycling. Okay, in case of recycling, this is how you can perform material balance. Okay, then since we are discussing with recycling operation, let's also discuss about another interesting operation, which is slightly associated with the recycling operation. And that operation is known as purging. Okay, that operation is known as purging. Okay, now what is purging? So let's say there are some inerts in this feed. Okay, let's say there are some inerts. And let's say this inert, it will go through the unit unaffected because it's inert, right? So it is going to go through the unit. It's not going to be affected at all. Then it is going to come at point 2. Here it would get separated. So if inerts go out of the process through finished products, then there is no problem at all. Fine, inerts have left the system, no issues. But the problem is that most of the time, the separator, it sends inerts back with the recycle stream. Okay, inerts are sent back along with the recycle stream. So what happens from the feed, fresh feed, you already have inerts coming in, which have no effect. There is no effect on these inerts. They are just as it is. All right, as it is going to go through the process. And then from the recycle stream as well, you have inerts coming in. All right. So at every loop, these inerts will keep on getting added. For example, for the first time, let's say recycle stream has come here. So this is going to be I, this is going to be I. This total is going to be 2I. Now 2I inerts are going here. Now these 2I inerts have come out. These 2I inerts have gone through this process. And now you have 2I plus I, which gives you 3I, right? And so on. These inerts, they will get accumulated in this process itself. All right, they'll get accumulated in this process itself. So in order to avoid that, in order to avoid the accumulation of inerts within the process, in order to stop the inerts from getting trapped within the process, we use the operation called purging. All right, we use the part called purging. All right, so purging is basically, in case of purging, from the recycle stream, this is the recycle stream, right? So from the recycle stream itself, let's say we take a particular point, let's say we are taking this point. So from this point, we take a stream and send it out of the system. Okay, we take a stream and we send it out of the system. So in this stream, you have almost all your inerts. Okay, in this stream, you have almost all your inerts. So this stream is known as the purge stream. All right, this stream is known as the purge stream. So this is a very, very important unit operation, because if you do not have a purge stream, if you do not conduct purging in case of inerts, if there are no inerts in the system, then that is not a problem. But if there are inerts in the system and you do not have this purge stream coming out, then in that case, your inerts will get accumulated within the system and they will lead to system failure. All right, they will lead to system failure. So that is why it is important that these inerts are removed from the recycle stream, and that is done by using a third stream, which is diverted using the from the recycle stream, and that purge stream, it contains most of the inerts. All right, so when purging comes into picture, then this overall material balance diagram that we drew, in this overall diagram, this blue diagram that we drew, so in this diagram, even the purge stream is going to be shown. Okay, even the purge stream is going to be shown in this diagram. And similarly, over here in the unit, there would be no issues. All right, there would be no issues in the rest because uh, only it's in this overall diagram that you need to show. Rest, nowhere inerts are actually not going to affect as such, because let's say here, this is the inert that is coming from the feed stream. I'm talking about junction number 1. So if inerts are coming from the feed stream and R, it is generally made free of inerts from the due to the purge stream. So the mixed stream, it will contain I inerts itself. And if we go to the second, if we go to the unit, then this I would, as it has come here as I. And then when we come to the second junction, junction number 2, then all this I will come out here. Okay, so as such, there would be no difference except for this entire unit where a purge stream has to be shown separately. Okay, it needs to be shown separately that the inerts from the fresh feed, these inerts from the fresh feed, they are not in the product, so they are accounted for in the purge stream. All right. So once you have this thing along with you, then it's very easy. All right. And one more equation can be found. Let's consider this point from where your purge stream has been taken out. Let's consider this point as point number 3. So for this point, you're going to have your another equation. So over here, you will get the recycle stream. Over here, you will get recycle minus inerts. Okay. And these inerts will be gone out from here using the purge stream. So this third stream, which contains inerts, it is the purge stream. All right. So over here as well, you can have a scope for material balance in case of purging. All right. So it's a very interesting unit operation and also it's slightly confusing. So make sure you understand the concepts behind purging, why purging is done, what is the use, and all those things. All right. And now we come to another unit operation, which is bypass. All right. Now, what is bypass? So let's say you have a stream. This is your feed stream. Okay. And it has to go into the unit. It has to go to the unit. All right. And from this unit, it is going to come out as the product. All right. Now, let's say your feed stream, it contains A and B. Okay. So let's say this unit is suppose a distillation column. I'll explain. Suppose if this unit is a distillation column, or let's not go to a distillation column. Let's say this is a unit where it is being severely heated. Let's say it's a furnace, okay, or a kiln or something like that. So it's this mixture that is entering this unit. It is being severely heated. Okay, severely it's being heated. So if this is severely heated, and let's say out of A and B, let's say that B is not tolerant towards heat, it is going to get damaged, or it might react, it might something else might happen with B, right? So it's heat intolerant. So therefore, if we definitely have to heat the stream for some reason, and we cannot simply afford to heat B, then in that case, this B will not be made to pass through this unit, while only A will be made to pass through this unit. All right. So how is that done? This thing is done by, from this point, let's call it point number 1. From this point, a stream is taken out, which contains all the B. Right. A stream is taken out, which contains all the B. And then this B stream, it comes and joins the processed stream at point number 2. All right. So that's how you are going to have your bypass operation. Something like this you will see. So again, in case of a bypass operation, there are various scopes for a material balance. For example, here, if I draw a system boundary, right? If I draw a system boundary, a control volume, then in that case, the material balance can be done, right? Similarly, I could also form equations with respect to this unit, all right, with respect to this unit. Also, we can form equations for junction number 1 as well as junction number 2. Okay, so we can form equations for 1 and 2. So we'll have 4 equations and we can simply solve problems using bypass operation. So hope you people are clear with recycling, bypass and purging. In recycling operation, a part of the product stream is sent back to mix with the feed stream in order to increase the efficiency of the process, right? In bypass, a part of the feed stream is diverted and it is not made to pass through the unit, okay, and it is merged further with the processed product, right? With the processed product it merges, right? That is the bypass operation. And finally you have the purging operation, where from the recycle stream itself, a small stream, it is diverted. The stream is diverted because let's say there are inerts in the feed, so they'll get accumulated in the process if they are present in the recycle stream. Therefore, these inerts from the recycle stream need to be removed, and that is done using the purge stream or using purging. All right. So purge, these three are very important terms that you need to keep in mind. All right.